high-tech solutions. Yeah. So the notion that you solve are driven by that. I was also in the article says the following. The system, find a motorway system, you'll find a road system. These infrastructures are very, very expensive, and they were expensive to build, and they were built over a long period of time. The modern infrastructure is an information infrastructure, and it's a lot cheaper to create, and in many African countries it's advanced, so advanced, or even more advanced than the UK. So the notion is, if economies are going to develop where they don't have the physical infrastructure, but they've got the information infrastructure, how's that going to happen? And basically that's going to happen because of you lot understanding how to best make use of that information infrastructure to deliver solutions. That's the gist of the article. And I think the philosophy of the meeting. So for a machine learning example, what I thought I'd start with is the project that, so I visited John and Ernest and Martin in Makerere University in Kampala, and the AI dev group that had been set up there is still going strong. Many of the people here from that group back in 2013. And we were, well, I was interested in, on the modeling side, in temporal-spatial prediction models. And Ricardo, who was my PhD student, and Martin, who was John's PhD student, we started collaborating together looking at malaria incidents in Uganda because we had this HMIS data, so from the health centers about what the prescription of drugs was, and we also had so-called sentinel site data. So here's one district in Uganda. This is sort of, you get these maps on Wikipedia. And so for each of these districts, we had measurements of incidence of data. In that particular, that's not Nagongera, but Nagongera has what's called a sentinel site. So a sentinel site is where the World Health Organization has gone in and very carefully measured malaria incidents. But alongside this carefully measured, and those you can't see them very well, these are the carefully measured incidents of malaria. We have this HMIS data. This HMIS data is for patients' prescriptions. It's what like health centers are reporting, but they didn't really, they just gave them the drugs, and they may have had typhoid. We don't really know. And that's aggregated at some district level. So our idea was, could we use the sort of HMIS data and the sentinel data, combine them together, and also use things like rainfall and temperature to try and get a better, more accurate idea of malaria incidence. John's looking slightly critical. Was that our idea? Yeah. Yeah. And this is before DSA existed or anything. So here's another district, and here's sort of a couple of measures of this. This is like trying to predict into the future some malaria incidents. In one case, just using what's a model called a Gaussian process, a regression model to fit for the data, and in another doing something we call co-regionalization. Co-regionalization is where you borrow information from neighboring districts. And that was the idea of Ricardo's PhD thesis. He was working on that. And this is like, I guess, the origin of Data Science Africa is that we started with this data science, this Gaussian process school in Makerere back in 2013. So hands up if you were there at the school. I think it's probably only me and, there we go. And there's Martin as well. There's John. John and me somehow disappear into the background. There's Ricardo, who's my PhD student, and Martin. And we just had a small group. John organized it. We had a number of master students. We had people from the Uganda Viral Research Institute. And we just did the same thing, probably the same thing we're doing here, but just 3 days of summer school, and or 2 days, wasn't it? Because we had Ramadan interfered or something. And after that, we set forth on this project. Now, here's the outcome of the project, which is rather different. Or this is there's actually, John can direct us to the website where the actual outcome is. Rather different from what we originally envisaged for a number of reasons. Many of those reasons are based around the data. So what we found was we got a negative result when we did the data until after Ricardo had finished his PhD and had written it up as a negative result. Then I said, look, why are you looking for a job? Why don't you visit John? We had a bit of funding. So he visited John and Martin and the UN Global Pulse and suddenly got access to the disaggregated data. So the HMIS data was aggregated across the district, and now he got access to the disaggregated data. And what they found out is the data had been aggregated with missing values in place. So that basically had destroyed the data. So the data we were working in was broken in a severe way. And when they redid the analysis on the disaggregated data, it worked. But that wasn't actually the important thing they did. But the analysis worked when you got closer to the data. That's important lesson number one. You are not going to get a situation where people taking data out of the country doing the analysis from 2,000, 3,000 miles away are solving the problems. You have to be close to the data. Everyone talks about machine learning models, but you have to be close to the data. So it worked in terms of what I think was done was, instead of the more ambitious thing we'd done is that they built a project to fill in the missing values in the reports that were coming in and give a better visualization. The visualization I'm showing here isn't the visualization that was used, but this is Ricardo's idea that I like. Give a better visualization in the Department of Health and for UN Global Pulse about where malaria was in the country. So a fairly simple thing. Now, this wasn't implemented, was it, John? This thing, but I like this thing.
Not real time.
Not real time. Implementing stuff, by the way, there's a big difference between implementing stuff on your computer and implementing it real time. And if you want to implement something real time live, implement the simplest thing you can think of. Visualizations, as you're going to hear next, are always the right answer, like always. Because interpreting a model, the output of the model, is hard. A well-calibrated, well-designed visualization for the Ministry of Health or for the Ministry of Agriculture gives them way more information than some output from a neural network. So below that, there may be lots of neural networks going on to get that right, but visualizations are massive. And this one is something that Ricardo built, where over time, what you see, you might be able to make out, there's a red line, this is a GIF here. And the red line is the average sort of long timescale trend. Now, in a Gaussian process, which is the model Ricardo used, he's also modeling the short timescale trend in the blue line here. And then he's come up with this lovely visualization, which isn't implemented real time, as we know, but probably should be. So what this visualization is trying to show is, on one axis, it's showing the gradient of change, and then the other, it's showing whether you're above or below the average. So if it's green, the curve, this is one district of malaria cases. If it's green, you are below the average trend, and you're going down, like just, it was doing that for a moment there. You're below and things are going down, that's green. If it's yellow, you're below the average trend, but it's climbing. If it's red, you're above the average trend, and the malaria incidence rate is going up. And if it's orange, amber, or whatever we call that color, it's above average but going down. So very, very simple. I mean, the modeling's nice, it's sophisticated, but a simple idea which suddenly gives you the ability to convert what is a curve that is difficult to interpret into a map across Uganda. If it's grey, the effect is too small. Right, so Ricardo did this. I might have preferred it to be a circle or something, but you know, that's a design choice. So this is the map of Uganda across the districts. Okay, these funny things are because it's going into Lake Victoria. We presume the malaria doesn't really go into Lake Victoria. But there's the map at any sort of given time progressing. So you've got an immediate visualization of what's going on in the country. Some simple modeling followed by a visualization. And I think that that's the type of solutions, for me, I mean, there's other solutions that make a difference, but these sort of solutions make a big, big difference. Now, I would argue that, I mean, maybe there's somewhere in the world, but it's very, very rare to be involved in an organization that is capable of going from the data sourcing to the visualization. Like, I always think of it from the field to the ministry. From the health centres to the Ministry of Health, from the farmer's field to the Ministry of Agriculture, in terms of giving the information. It's extremely rare. We've got ARM here, you're going to do practicals on IoT devices, right? Actually sourcing the information for them. A massive inspiration project for me is Ernest's project. and many others involved, Daniel, others, with the sourcing of information in the field through photographs of leaves with whitefly and automatically counting the leaf and getting the cassava information beamed up to the ministry. These projects make a really big difference. And not only that, while we don't have to always use the latest technology, in terms of the end-to-end nature of it, it's unique. I have learned more about how to deploy data science in the real world through Data Science Africa than anything else I've ever done. Because it's the only place, ironically, it's that lack of existing infrastructure that enables this. The fact that this was difficult to do before, the fact that even filling in, I remember the email John forwarded me from the Ministry of Health, that even when just filling in the missing data, the visualization, not this visualization, just the visualization of the rains, she said this is going to be vital for us as the rains approach in terms of our medicine distribution policies. You know, you can make that amount of difference with relatively simple things, but you have to do the whole thing, and that's the whole point in end-to-end, which is like a recurring theme for us. And you learn more, I think, about the real bottlenecks of Data Science Africa than anywhere else. Maybe there's somewhere else, I just don't know where. Okay, so that's why I think machine learning is interesting, but I only find machine learning interesting nowadays. Everyone's doing machine learning. If you go to Europe this next year, there'll be 14,000 people there, right? How much of them are doing things that interest me? Relatively few. I don't need to worry about people creating new machine learning models anymore. There's 14,000 people. There used to be, like if you go back 10 years, there were like 600 of us or something. Then you had to worry whether people were going to use this. You don't have to worry about that anymore. Don't worry, if you don't create machine learning models, someone else will. It's the sort of monkeys typing Shakespeare type effect going on, right? You know, eventually someone will get to it. So you don't have to worry about it. But what you do have to worry about is why. Why are people doing this? They very rarely motivate what they're doing by any application. They very rarely think about the context. And that's because it's isolated from them. They get given a data set, they work on that context, that data set in isolation. None of you are isolated from that. So machine learning in that context is really, really important. So the rise of machine learning is driven not by how clever we were 10 years ago, to be frank. It's driven just by data and computation. Because it's a combination of modeling techniques, sorry, there's an extra plus there, modeling techniques, many of which, the neural network ones, were already in the field when I joined in 1996. People had already proposed these things, so apparently I had no effect on the entire field. But what did happen is the availability of data and compute went up massively, and we need that compute to make predictions. Now immediately you see this, you see that there's two parts to this, and everyone talks about models the whole time, but data is, I would say it's clearly just as important, but I would say it's even more important in terms of driving your ability to get good predictions. And you can also see that other things come in. So bias can come in here, bias can come in here. So you can create fairness and bias problems around the data you collect, or with the model you use, right? So that's the way I just think about machine learning. And it's important to understand modeling techniques, but in the end, if you're interested in good, unbiased, accurate predictions that make a difference, you should not really care too much about what model you use. Personally, I have lots of feelings and beliefs about the models I'd like to use, and that inspires the sort of research I do. But fundamentally, it's an empirical science. Things are driven by results. So what's driving the phenomena we're in? Well, we're the people, this is the data. In the old world, we didn't have these. And we have a very narrow bandwidth capability to interact with data. So classical statistics was all about us interacting with data in the days when data was rare and our bandwidth was low. So it was about statistical design of experiments. With the computer in the equation, there's a massive bandwidth connection between the computer, whether that's our mobile phones, whether that's our desktops, whether that's the cloud, and the data. And now, to a large extent, we're observing data via the computer. So the computer's becoming a mediator of the data. And I would argue that that's a large part of that is happening through machine learning. So there's a big opportunity to do this better or to do it worse. And when you see things going wrong in society, people saying things like, oh, elections are being manipulated, or hate speech, or whatever else, That's people using the computer to manipulate this in a bad way. So the duty is on us, I'm afraid. Maybe some of you want to do it in an evil way. Okay. You could probably make more money. The duty is on the rest of us to try and ensure this manipulation is happening in as good a way as possible and is as representative as what's going on so that humans are well informed and make good decisions. That involves so many things. That doesn't just involve getting the data out, cleaning it up, doing the model. It involves understanding how humans work so you present the data in the right way. If you don't do that, it's becoming more and more important that you understand how a human is going to interpret the data. It's not good enough just to say, here's the result. I mean, in the UK, there was this comedy skit where every time someone would be working at a computer and someone would ask them a question and they would just say, oh, computer says no. Sorry, computer says no. No, because that's the sense. We don't have a good model, and that link's kind of broken at the moment. So here's something to me. This is Sheffield, right? I used to go running here very often. What I love about this is this thing here is called Packhorse Bridge. It's called Packhorse Bridge because it used to have pack horses going across it. And it used to be the main route going from like the west coast to the east coast across Sheffield for many, many, many years, well into the 18th century, right? So that's the sort of infrastructure people had at one stage for moving goods around, okay? Now, I find it amazing when you look at modern infrastructures, how quickly they've developed around economics. Like, what was being moved here was things like iron ore going into Sheffield to make steel goods, right? On the back of a pack horse. Or steel goods going the other way. Very, very, I mean, it blows my mind how these things scale and how economies build bigger things. But one of the things that in my, so this is Cromford, so this is just down the way from Sheffield, this is the Derwent Valley. Cromford is the location of the first factory system, and this is Cromford Canal, which was built. I find that mind-blowing as well, the fact that you got sort of, actually it was Irish that they would bring in to dig canals. Large-scale people digging canals by hand. The transport of goods, they were making enough money out of the transport of goods to be able to dig canals to send boats up hills, you know, to move stuff around because transport is so important. And of course that's a massive problem, say in the African context, that actually very often the road system isn't very good, transport of goods is harder. But of course what these people were lacking almost entirely was information. So information was only traveling as fast as the goods. So ideas about where to send the goods and those sort of things were missing. So one of the projects I find very inspiring is again one coming out of Kampala, the Kudu project, which is really about having an information infrastructure above the transport infrastructure to make sure that when people are driving agricultural goods, they're driving them to the right town. So they sell the goods before they set off in that idea. So you can immediately see how information movement is reducing the need for physical infrastructure. Also, the mobile money, again, Jesus said. That, you know, when you talk to people that say, I used to have to drive 5 hours to my village every weekend to deliver cash, and now I just send it by a mobile phone, you can see how information is saving the need to use the physical infrastructure. So clearly you need physical infrastructure. But as soon as you're moving information instead of just stuff, there's so many opportunities to very cheaply do things. And you know who's best placed to take advantage of those opportunities? You lot. Because again and again and again, you hear systems coming from outside the country or outside the continent saying, oh, this is how Africa should work. And it's always rubbish. It's always some stupid idea. But as entrepreneurs, as people with this new power, this capability, mobile phones, you're very, very well positioned to come up with the right ideas to deliver for the context here. If you look at what's happened in the rest of the world, in terms of the transport ecosystem, globalization has been driven by that. That is a container. The reason why, so this is one of my favorite little, so this is wild Alaskan Pacific cod. So this is cod that's caught off Alaska, and it's being sold in the Northwest United States, frozen. The best bit about it, it's wild caught, but yet it's a product of China. How is that possible? That's possible because this vast infrastructure of containers and transport has meant that between the United States and China, it's cheaper to send the cod to China for manual processing and send it back to the United States in containers. That's the world, that's what's driving globalization. Everyone says it's this or tariffs or that. No, it's down to the fact that transport costs are like orders of magnitude. If you've got an established transport ecosystem with containers, lower than processing costs. So you send goods to where processing costs are cheapest, and then you save money. And that's happening all over, right? In terms of large scale, anything that's manufactured on the large scale. The only thing that you can do to compete with that is where you've got things that are being driven by a local economy or for local reasons, right? So, for example, Scottish whiskey, has to be made in Scotland. People want it. Tartar, those sort of things, local goods. All those sort of businesses are doing very well. They're unaffected by globalization. I think there's a big lesson about that for developing economies as well. That wherever there are local skills and they can be leveraged through information, that's a really interesting area to work. So one of the areas I've been working on in the last year and a half, my team's been in Amazon supply chain, and I would say Amazon supply chain, which is a highly automated, information-driven supply chain, is probably the world's largest automated decision-making network. So I would say it could be the world's largest AI in terms of money spent on a sort of weekly basis. And we have this big challenge that so much of it is mechanistic in terms of what happens in supply chain, but machine learning is really a data-driven technology. So for me, I see that the future, the near future of a lot of African infrastructure is going to be dominated by information. And so the knowledge of how you do that is really, I hope it's being taught here, and I hope you're also going to teach it, because that's what's going to open up the opportunities for people to develop new businesses around this space. So, let me skip those a bit. So, does anyone know what's important about this district? So this district is the home. Was it? Go ahead. Was it?
So it's home to our first gold medal since 1970. Oh no!
Very important. One of the other things Uganda is famous for is marathon runs.
Then Ethiopia.
That's the home district of this very important Ugandan called Stephen Kiprotich. I don't know any other countries that are good at marathon running. Are there others? This guy won the big marathon in London.
Yeah, he was an outlier.
Well, he's actually, I think you can tell from his name, Kiprotich, he's part of the same tribe that all the...
basically a Kenyan.
But we're agreed that it's Kenya and Uganda, right? There's nowhere else really good marathon. So actually, this example I keep using because I developed it when I first gave some of these slides, not the slides I'm really giving today, in Uganda in 2013, just a year after Kiprotich had won the marathon. And yeah, so it's Akibua is the other gold medal for the 400 meters hurdles, is that right? 100 meters. Yeah, and I remember that because my hotel was Akibua High Road, I think. No, 2 gold medals. Data, marathon data. So this is, I think that this really fast time here is that 2000. So he's slightly slower. That's the fastest ever. There's another one that I haven't added yet, but that's Kiprotich there. So it's showing the data up to when Kiprotich won. But the reason I find this data interesting is it goes right across the Olympics, and it has some interesting characteristics. It's descending over time, and it's got this outlier. And if you investigate this. This is a time series which we might want to predict, like we want to predict the malaria over time. And in this case, this outlier is due to the fact that in 1904 it was organized in the United States, and they had cars leading the marathon for the first time, and all the roads were dust, so they kicked up a lot of dust, and everyone choked on the dust, and then they all got lost. And so only 6 people finished, And this time, this is a very achievable time for even an English marathon runner like me. But, you know, it was, everyone got lost, so it's got this interesting outline. So this is the pace of the marathons, right? So you can see the pace is coming down. I think, I can't remember the exact pace, but it's 42 kilometers, so trying to do it in less than 2 hours is, you know, 2 hours would be, 3-minute pace would be 126 minutes, so you're under 3-minute pace. Now, if you ever, by the way, if you have ever tried to just run a kilometer at under a 3-minute pace, then, you know, like in the regular Sheffield Park run, the best marathon runners in the world would just win that park run by a mile 8 times in a row, which is just extraordinary. I mean, keeping that pace for anything over like 200 meters for normal human beings is pretty hard. This is a typical, well, it's quite a fast pace for 10K that one actually. Okay, so, and what we do is we fit functions to that data. So what I'm showing you here is polynomial fits to the data. So the whole idea in machine learning is we're given some data like this, but we want a mathematical representation of the data. It's just a way of automating. Forget all the models, all the neural networks and everything else. We've got some sub-process we want to automate where the data is often being generated by humans, or we need to recreate it in some way. We don't know exactly how it all came about, so we're trying to fit a mathematical function. In this case, I'm just fitting a straight line. But we can fit other mathematical functions as well. So this is a quadratic fit to that data. And in each case, you can look at it and think about whether you think it's plausible. You might be interested in one or two things. So you might be interested in what's the marathon time going to be in the next Olympics, which will be what, 2020, next year? Or you might be interested in another question. So one question that interests me is that Alan Turing was not only an amazing computer scientist, cryptographer, and general all-round very clever person, but he also ran in 1946 the marathon in the UK Championships, and he came 10th with a time of 2 hours 46 minutes. Now the time in 48, this one here, which is a bit of an outlier because it's just post-war, was I think 2.5 hours. So you can ask the question, what's the probability that Turing would have won a marathon had the Olympic marathon had it been run in 46, like given that time? You know his time in 46. I mean, he was 10th in the UK Championships. But you can ask that question, and that's an interpolation question. So you've got two questions here you can ask, an extrapolation or an interpolation question. Interpolation is moving between the points, trying to sort of say what happened between two of the data. Now, extrapolation is notoriously difficult, where you're going out into the future. And you be very, very careful with extrapolation. Before you extrapolate, you generally want a mechanistic understanding of what's going on. So an example of an extrapolation problem would be, let's say I've got a supply chain network and I choose to build a new warehouse or a new factory. I have no data about what that will do. So I have to have an understanding of like how that supply chain is connected and a belief in what that will do to my demand and so on and so forth. I can't do it from data. That's an extrapolation, right? Because I don't have that fulfillment center or warehouse in place. But you can do a lot of stuff where you're moving between data you've already got before. And that's where machine learning works well, is interpolation. What I'm showing you on the right is the so-called sum of squared error as we, the wrong thing, as we increase the order of the polynomials. So this is a polynomial curve, but what I can do is I can increase the order of the polynomial a great deal. Now what do people think? Which is the better fit? Look at this one. Okay? That fit there has 0 error. Is that a good fit? No. Why is it not a good fit? Someone want to tell me? It's overfitting. But what does overfitting mean? So that's what we call it, yeah.
It fits to generalized users.
Pardon?
It fits to generalized users.
Yeah, so it's doing really well on the data points themselves, but it's fitting to the underlying noise, and it's going in strange directions between them. So it's not, we wouldn't believe that would interpolate very well. We probably don't believe, I mean, Alan Turing's in, basically, if he'd run the marathon in 1946 according to this model, because he's about here, so he would have won. So we don't really believe that, because it's sort of, we call it overfitting, which it seems like a very good term when you see something like that, because it's like you've bent something, you've tried to fit it too much to the data. I think it's a difficult term in more complex scenarios. But basically, it's a situation where your training error is very different to if we had test data, and we'll come back to that later on. So, okay, I want people to sort of say what fit do they like. So how about, let's go back to this one. Here, how about that one? Good? Yeah? Is that better or worse? Pardon? Hands up if you think it's better. For this, well, actually good. See? Yeah, for which problem indeed? So actually, interestingly, they're not varying much. If you think of it, Daniel's asked exactly the right question. If you think of it in terms of the interpolation problem, so you look in that regime around 1946, I think you're not seeing very much difference. But look at it in terms of the extrapolation. Yeah? So this little tail flicking out here. Yeah? Flicking around like that. So now that's another, we'll look at that one. So that's flying up the extrapolation. And then we're down to the linear. So that's the quadratic, and that's the cubic fit. And that's the quartic. So the reason this is going down is because the cubic fit tends to have this sort of a shape like that. So you're encoding information about what you think the shape is in the polynomial function. And polynomials, by the way, are not a good thing to fit. They're not a good thing because those shapes are often not things you believe in. They're very analytic to fit, but you don't normally believe in shapes like that. So what we're seeing here, this little tail here is coming from, this is the quartic. So the quartic is happy to go up. So it's coming from the difference between what we're saying in the model. So data is controlling what's going on here, mainly for these orders of polynomials. But this extrapolation is very sensitive to model choice. It's always important to remember. Okay, so what machine learning is doing, how does it work? Well, we're taking a quantity of interest and we're trying to convert it into a mathematical function. So here, I'm sort of assuming what I'm interested in is whether someone is likely to, so they're on a famous e-commerce site, and we want to know whether they're likely to be interested in buying a sweater or a jersey or a jumper. It's a bad choice of word because in different variants of English people use different terms. You know, something for keeping you warm. So in this case, what we're going to decide is, as you get older, as I know, you feel the cold more. So the older you are, the more likely you are to want to buy a sweater. And also, the further north you are, typically, you want more likely you are to want to buy a sweater. I mean, we could add altitude in there, I'm thinking, since we're here. But let's just assume latitude and age. So what we're sort of saying, so first of all, we're just decomposing the problem to the probability you buy a sweater divided by the probability you don't buy a sweater. And that's known as the odds. That's the odds ratio between the probability of yes and the probability of no. And what we tend to model, this is a very statistical model I'm showing you here, and I'm using beta to sort of highlight it. It's a model from statistics. This is something called logistic regression. When I use beta, it means I care about the parameters. It means they're meaningful to me. If I use W, it means I don't care about the parameters. It means I'm just using them as a means to an end. Here, so somehow apparently I care about the parameters. This parameter is your sensitivity, your age sensitivity, and this parameter here is your latitude sensitivity. They're very interpretable because it's a linear model. And you'll see linear models being used a lot, not because of their predictive capability, but because of their interpretability. So if beta is positive, then the higher your age, the higher your odds you're going to buy a sweater. And this is a logarithm of the odds, so log odds, and that's a monotonic function, so the higher the log odds. Okay? And same with latitude. Now, of course, there's immediately something wrong with this model because some of the African continent stretches north and south across the equator. So latitude as measured around the equator, this model starts to go wrong because also as you go further south, people are more likely to want to buy sweaters. So that's an incorrectness in the model. So locally in the north, around the UK, maybe this model is right. There's a local linearization. But as you move outside that regime, that parameter is going to flip. So you've got a couple of things you can do. You can either come up with a more complex representation of latitude, which could be something like distance from the equator, right? So instead of measuring latitude, you could measure distance from the equator. And then that would make the model better. Or you can try and build nonlinear models. Now, a statistician would naturally go down to try and make this into something which is like distance from the equator, so they can keep the model linear. But in machine learning, we've cared typically less, although this is changing a lot, about the interpretability. And we tended to worry about the predictability of the model. So we tend to sort of, let's make it nonlinear. The problem with going nonlinear is it destroys the interpretability somewhat. So first of all, there's two stages to nonlinear. So these are called generalized linear models. They're called that because this thing here, we're interested in the probability of bought, right? But really the thing on the left is the log of the probability of the bought to the divided by the probability of not bought. And if we actually try and rephrase that in terms of what we're interested in, the probability of something being bought, what we find is the probability of being bought is related to a nonlinear function of a linear model. It's called a generalized linear model. And this one's called logistic regression. The functional form here is simply the functional form for the sigmoid that we should know from neural networks. So the pen here.
They're in your.
Here, this one.
Oh yeah, got it. Okay, thank you. So the functional form is this 1 over 1 plus e to the minus x. Well, I should say e to the minus argument of what's inside there. Oh yeah, let's call that x for the moment. It's that form, which is this sigmoid form. So if we were to draw it on an axis, it starts and it goes through 0.5 at the 0 and it saturates at 1. So it goes between 0 and 1. As you might expect, because it's a probability, probabilities have to be between 0 and 1. So it's taking some linear function on the input, and it says, if that linear function is positive, then it starts to go towards probability of 1 that someone buys a sweater. If it's negative, it goes to start towards 0. What might be wrong? This is a thought, this is a quick question with this function in this case. Specifically thinking about the probability of buying a sweater on an e-commerce site. What seems a bit dangerous here? Is the probability of buying a sweater in general, is it high or low? It's low.
Online, you're just putting your data out there into the
It's very, very low, actually. So it's it's what we might call a tail event in some sense. So which region on this curve are you actually using? What would you expect? If it's going to be very low, how is it very low, by the way? If this is positive against age, because it has to be increasing with age, and this is positive against latitude, what value causes it to be low? What means it's low? Because if this is positive and this is positive, that puts us on this side of the half space, and this is 0.5, so it's going to be over 0.5. So what's meaning that the sum of these things is not positive? What have we talked about? Huh? The bias, yeah. So it's called the bias term sometimes. Yeah, this beta 0. So what's this thing going to be? Pardon? Well, it's like negative. So you're right, I know what you mean in terms of like, if we remove that, if it was 0, the answer would be 0.5. But to drive the probability of being bought low, it has to be negative. So if we didn't have that, then we would be in the positive half space here. If we have that back in, it takes us, like, it recenters everything. So it sort of moves that curve to the right, and it means we'd be operating in this region down here. Now, if you know you're going to operate in such low probability regions, you might want to do work something that's where you're not worrying about this part of the curve. You might want to do something more sensible than that. And there's a lot of work on sort of tail events, which uses different models from this one. So you always have to think about your model. So this is called logistic regression, and very often instead of writing it in this way, we might just think of those inputs as a vector of features, which might also include altitude, might include a number of other things we were interested in, and use that to predict whether someone's going to buy or not. By the way, that model is, or was, I don't know if it still is, but at one point it's being used to rank your news, Facebook newsfeed. But the features it's using are things like how close you are in friendship to the person whose post you're seeing, whether or not there's an image. If you want your Facebook posts to go up, it used to be that you had to put an image on them because people like posts with images better. Humans like images, apparently. So the newsfeed ranking once was all done by something like this with regression trees behind it. Logistic regression on top of something called regression trees. There's a paper about it you can read online. But machine learning, all it's doing, we can simplify that, it's taking something we're interested in and it's relating it through a mathematical function to some features we have via some parameters. Yeah? And that's generally what machine learning is doing, almost always. There's some exceptions, things like, say, k-nearest neighbors is a little bit different, or decision trees are a little bit different, but most algorithms this applies to. So I call f the prediction function. Now what you'll hear nowadays, in a terrible turn of events, everyone calls that inference now. But it's horrible that they did that because inference actually means something totally different in statistics, and I don't know when it started meaning prediction. But when you hear people talking about inference in neural networks, they mean just running this mathematical function forward. Yeah? And neural networks are quite large models, so even that is quite slow. So everyone's worried about doing that in hardware now. How to build hardware for inference. Okay, but how does it match the data? Then you use an objective function. So there's two parts to machine learning, two mathematical functions. The prediction function is basically the function we've been looking at that goes through the data, and the objective function is measuring how good that fit is at any given time. So the least squares objective says, let's look at the training data. So this is the times from the marathon. Sorry, the pace from the marathon. This is the year the marathon occurred. And this is a linear function in that case. And beta would just be, this would be mx plus c, basically, with m being a gradient if it's linear, or it's a polynomial. And then what you do is you try and minimize the sum of these squared errors. And that's, if it's linear, people do that in high school. All that's going on in the wonderful world of neural networks is much more complex functions. So why do we put more complex functions in? Why do we have such crazy functions? I'll throw that out there. Why have we moved away from this type of thing? What sort of things are neural networks known to be good for? What was that?
Functions approximation.
Function approximation, yeah. But what particular inputs? Where have we seen all the big breakthroughs in recent years? Images is a really big one, yeah. What else? Images, what else? Audio, yeah. Language would be another one. Yeah. Now, it's much harder. People did this for a number of years, to take images and come up with the equivalent features of latitude and age, right? So people have tried it. There's something called SIFT. If you want to look at the one effort to do it, which was very, very successful, drove a lot of machine vision for a number of years, a feature select called SIFT. In fact, did you use SIFT on the first version of the whitefly detector? Yes, there's some nodding going on here. And what does the current version of the whitefly detector use? CNNs, conv neural networks. So these people have lived this revolution in machine learning. In the SIFT was a very lightweight computer vision technique that allowed people to do image recognition fast on mobile phones, as was being done for this agriculture project. But now people are capable of doing convolutional neural networks on that thing, and the accuracy is a lot better. And the accuracy is a lot better because those images not only are they hard to come up with features for, we can say some interesting things about images. So we can say some interesting things like, if I'm standing, you're all seeing an image here. Don't move your heads. Keep all your heads fixed firmly on me. Don't move your eyes. I know it's hard. I'm going to move over here. Did I become a different person? No. That's called translation invariance. Also, if I do this, I don't become a different person. That's called rotational invariance, right? So there's all sorts, I have all sorts of invariances. Scale invariance, yeah? It doesn't bother you at all. What may bother you is to know that those convolutional neural networks, with all that funky stuff they're bringing, all they're giving us is translational invariance. It's shocking that just translational invariance is all we're getting. They're not giving us scale invariance, that's learned. That has to be learned within the model. I mean, they're not giving us rotational invariance. So all that work on these very funky functions is being introduced to do something very simple, which we take for granted. In terms of audio, there's temporal things going on. There's temporal structure in audio, which RNNs are really good at picking up. And those very complex structures, again, dealing with the temporal structure. Okay. So I've talked through all that. So let's have a look at what these look like. Oh yeah. So it's intro to machine learning, and if you look at the notes I told you, that they're split into three parts: supervised, unsupervised, and reinforcement. And you know, everyone wants to do reinforcement learning. The number of deployed applications of reinforcement learning in the wild is so vanishingly small, it's approximately zero. Now, that doesn't mean reinforcement learning is not interesting or won't be interesting in the future, and that we won't be overtaken by killer robots all running reinforcement learning algorithms. But basically, think very, very seriously before you try and use reinforcement learning to do something, because typically it's not required. In fact, we have a name, when reinforcement learning is working, we have a name for it. It's called control engineering. Working reinforcement learning is called control engineering. Control engineering that doesn't work is called reinforcement learning. I joke, but there's a serious point there, because control engineers focus very much on, control engineers are moving big things around like cranes and stuff like that. If it goes wrong, people die. Heavy things are being moved. So in control engineering, they focus very much on the worst case performance. Worst case performance meaning they analyze and they prove the controllability of the system, and they prove that it won't oscillate. Reinforcement learning is typically looking at average case performance. It doesn't matter if you make a wrong move in Go, right? You lose one match to the world champion, and everyone talks about, oh, you know, how it failed to think or something like that. But all that happened is you had an average case performance, and you got caught out. If you deploy that on a driverless car, someone dies. Yeah? That's why control engineers look at worst case performance. So what you're seeing at the moment is a lot of reinforcement learning may be being deployed, and we're looking at a lot of average case performance. But that's all empirical proofs that it works. And you know, I think it is interesting. It's a big area of research. But if you're talking about practical stuff, you're mainly in supervised learning. That's where the big revolution has happened around speech and language. And you know, perhaps some unsupervised learning comes in, particularly around visualization. Clustering is such a cool method to help people understand data. But I'm not going to talk about those two. I'm just going to carry on. Well, I'm already over time. So I'm just going to sort of finish on, try and give you an intuition about what's going on. So there's lots of applications of these things, particularly in around that work I was showing you on malaria is basically all supervised learning, right? There's some pre-processing, but it's all supervised learning. Trying to predict, given an input location and a time, what the malaria rate is. But let's talk a little bit about the neural networks, because I want to demystify them, because they are not like the brain, they're nothing to do with it. It's just embarrassing how much length we have to go to introduce one invariance. So we talked a bit about invariance, and what I'm showing you here is a picture of a convolutional neural network, okay? So it looks very complex, and there's all sorts of fancy things going on, but all this is function composition, right? So remember those little sigmoid things? It's not sigmoid, it's ReLUs, as you may know in this case. Well, and also these all these special units for doing the translation invariance. So at this point, all this stuff is to try and introduce translation invariance on that image. Horribly complex just to deal with that. This stuff is the fully connected layer, and it's just composition of functions, one function feeding into another. So sometimes I give public talks onto this, and I say, look, it's not complex, it's just like a pinball machine. So, that was a Callista Flockhart detector, in case you didn't know who that was. What basically goes on is you present a point to the neural network. And think of that as a pinball machine. You can think of your input as being one-dimensional. It's the position on the XY space of this machine. Now it goes to this next layer, position on the XY, it's on the X space, the X-axis, not the XY, on the X-axis here. At each layer, each of these set of pins we can think of as a function, because it comes in and it comes out at a different location. So if I put a data point through the machine, it starts there and it goes through, and that wasn't Callista, but it's classified it as Callista. It's fallen out of the machine on one side, the yes side. That's the equivalent to falling out on that side of this diagram versus this side, yeah? For that function. Here's a yes point that is being classified yes, and here's a yes point that is being classified no. So training in the neural network here, in our pinball machine, the pins are the parameters. So training in the neural network is moving these pins around. And really this analogy holds up quite strongly. That you've got these basis functions which actually have a different structure from this. They go sort of straight up there typically. And this location point can be thought of as the point of the pin. And what you have to do is move these pins around such that for the training data, those 3 training data we have, they all fall through to the right place. Now, the problem with this analogy is it's one-dimensional in, one-dimensional out, one-dimensional each layer. What you have to now do, well, number one, first of all, think about how many balls you would have to throw through this machine to prove that all the pins were in the right place. Quite a lot for even a relatively small machine. You would have to throw a number of balls through. That's equivalent to the number of data you're having to put through on the training to validate the model. Now if you think about, instead of a pinball in one dimension like that, you start thinking about pinball in many thousands or millions of dimensions with very high dimensional hyperplanes operating as the basis, right? That's why these models are so data hungry. And that's why, by the way, one of the most frustrating things I have is that people are surprised by these adversarial examples. Adversarial examples are these things where you change the input just by a small amount using the ball of space in this pinball machine, and then it comes out in a totally different space. As soon as you think of it in this way, it's kind of obvious that in this vast hyperspace of a pinball machine, with all these complex arrangements of pins, that you're going to be able to move things a little bit and they'll come through the machine in the wrong place. It's almost like a miracle that you get anything out of these things. They behave very weirdly in these high dimensional spaces, and you should have the intuition around that. The miracle is that they do work, and they work for a lot of tricks around stochastic gradient descent and dropout and all these things that keep the path where the data normally flows through very reasonable, or finds reasonable paths. So I had more stuff, but I'll sort of end there, because I think I covered everything I wanted to speak about, really. There's, as I said, there's notes online which cover all these concepts in more detail. So if you go to, if you search for Neil Lawrence talks, or you go to this website /talks, you'll see me covering all these concepts in much more written detail, and also some discussion of unsupervised and reinforcement learning to read in your own time. And I think you can even maybe access a notebook from there, which won't work out of the box, but with some fiddling you can play with some of these examples. So that's it. And any questions? I'm a bit over. Apologize.
Yeah, thanks very much, Neil. Any questions to Neil? Okay. Any questions? Yes.
So my question is about the pinball model we have. Okay, so how does that relate to not? Yeah, suppose you just knock it out and then maybe put and they decode the parts in the network. How can you visualize that? Does that notion still apply?
You mean like, yeah, so actually what would the convolutional layers look like in the pinball model?
Yeah.
Very, very different. In fact, that's one of the reasons it works. That it's not all pins, that there's a lot of structuring of what those pins look like to reduce the dimension. Fully connected. I just want to get people away from like brain.
Everyone is going to neural networks now. They're solving everything. What's sort of the role of the other types of networks? What does the future look like 5 years from now?
That's a great question. And I mean, I think neural networks are great and they're working across a range of areas. They have some serious weaknesses. But it's clear and obvious to me. People here know the story of King Canute. It's a British story. It's a king who was told he was very clever and wise and he could stop the tide. And he said he couldn't, but they made him sit on the beach and try and tell the tide not to come in. And he got quite wet. So there is a tidal movement at the moment that whatever the weaknesses of the neural networks, they're being so successful across a number of areas, and it's going to take us a while for people to genuinely realize those weaknesses because they're performing and doing a load of things we couldn't do before. So my suspicion is over the next 5 years, what you'll see is increasing dominance of that paradigm, and it's going to become more embedded because it will literally become embedded in our hardware. So you're going to see hardware solutions around training and prediction on these neural networks. That means that when I have a mobile phone, I will be able to run efficiently neural network, potentially training, certainly prediction on the phone. That's a game changer because it means whatever the best model was from an accuracy perspective, from an energy consumption perspective, the best model to ship on the phone is a neural network. So if you're not using a neural network, you're going to have to work out how your model really is a neural network before you ship it. And that's going to have a massive distortional effect on the area. So I think that the biggest questions, though, that's all inevitable. We don't have to, that's like the tide coming in. We don't have to come in and get a bucket and throw more water up the beach. It will come in on its own. So you have to sort of stand off and say, that's going to happen. What are we going to have to do about it? Well, a lot of stuff's going to get wet. So what we have to do is move above it. And a lot of the more advanced modeling techniques, we need for things like explanation, for dealing with things like when the neural networks are in regimes where they shouldn't be operating because they've never seen data there. You're going to need a layer of hypervision. You're going to need a layer sitting above the layer of these interacting neural networks doing all these things that software engineers have deployed, where you're worrying about the fairness of the system, you're worrying about the reliability of the system, and you're worrying about how to redeploy those neural networks when the world changes around it. So you're sort of going to have to fly off the beach and think about it from a sort of higher perspective. And that's where those models will come back in.
Yeah, I have a question on when it comes to production, which models do you recommend people?
So that's a great question. When it comes to production, which models do you recommend? So first of all, always ship the simplest model possible. It just happens. At the moment, what I see in terms of things being shipped, if you're in a domain like vision or speech or language, people are shipping neural networks. I have doubts when they're shipping neural networks. You know, it's always an interesting question to ask, did you try linear regression first? Because you should have tried linear regression first, even if you're going to ship a one-layer neural network. So there's this interesting thing, it's like, are you in the world of scikit-learn, where you've got decision trees and all this sort of other thing, or are you in the world of PyTorch, TensorFlow, MXNet? And I think for many, many things in data science, you're actually in scikit-learn world. But clearly, when you're starting to look at vision and speech and things like this, and there's some nice examples from projects coming out of people who are in the data science Africa community, like rare language recognition or the whitefly recognition, you end up using neural networks. So, but yeah, the simplest model possible. Because the more complex you make it, by the way, the hardest thing you're going to do is not to train a neural network. That's not the hardest thing you're going to do. The hardest thing you're going to do is get your system into production, into somewhere where it's actually being used live. And your decisions around simplicity will benefit you a great deal when you move to production. And the answer to Ernest earlier was really driven by the fact is it's going to become simpler and simpler and simpler to launch a neural network. So over time, that answer will change to, oh, use a neural network because they've already got the chip on Android phones and iPhones and whatever else. Palm in bed.
Friends that page maybe take greater care about statistics and things of that nature in the real world. Because I suspect that a great fraction of us don't really pay too much attention.
Yeah, that's a great question. Does it pay to care about the statistics? Yeah. So one of the things there was this big movement when Xerox, who made printers and copiers, they founded Xerox Palo Alto Research because they said the office of the computer will have no paper in it. And we need to be on top of that, and we need to understand the computers. So they developed the graphical user interface and all this stuff to think about how the office of the computer. But the truth was that the amount of paper consumption shot through the roof in the 1990s as everyone started printing information. Now, any idea that there's a reducing need for classical statistics with machine learning is completely the wrong way around. The need for statistics is growing day by day because it's becoming easier and easier to fit these models. So fitting isn't the problem. That's like, you can think of my best analogy is like anyone can program, but can they program well? Can they write good software that can be shipped? And the test of the good software is all statistical tests and all statistical knowledge. And understanding bias and fairness is all, and interpretability is all about the thinking I deploy on the model afterwards. So statistics for me was the most boring thing I studied in maths at school. And it's probably the most important thing to know about in this current age. Because it's much more static, right? I mean, you might know about TensorFlow this week, but next week you need to know about PyTorch or something else, right? That's all changing. The statistics is much more static, and it's all true. Randomized controlled trials, all these sort of things. A/B testing. I mean, it dominates the world around us. Great question. Okay, I'm already over time.
Thank you. Thank you very much. Yeah.